In this recording, we're going to look at how charged particles move in a magnetic field. Now, in the previous lesson, we were looking at charges that were inside a wire. Now, when the electrons are moving inside a wire, they have no choice but to move in a straight line with that wire. But now the charges are going to be single particles, such as a single electron or a single proton or a single ion. And that ion, proton, electron will be able to move freely inside this magnetic field. And what you're going to see is that instead of the particle moving in a straight line, it's going to have circular motion. All right, first of all, let's do a bit of a review of some of the equations so that maybe you can better understand the equation for the force acting on a charged particle. So first of all, hopefully you remember in year 11 that you had an equation for the current. And that equation is Q divided by T. Or you can use a small q over T. And Q is the charge in coulombs. This means, since current I has the units amps, this means that 1 amp is equal to 1 coulomb per second. So now what we're going to do is look at the equation for the force acting on a wire, which is ILB. But what we're going to do is we're going to replace the I with our Q over T. And then it goes LB. Now, hopefully you realize that when you're dividing the Q by T, you're actually dividing the entire equation by T. And that means that I can just move things around a little bit and I could have the length divided by T. Now, if you have length divided by time, what do you end up with? Velocity. If we have a constant speed, then the distance over time equation gives you QVB. And so this is where our equation for magnetic force comes from for a charged particle. So the next question 3 says, explain why you could use the same equation for a moving charge as you can for a wire. And the answer for that is that charged particles are moving through a wire. The only difference is that charges must remain inside the wire. So first of all, I'll write that. Charged particles are moving through a wire. Oops. The only difference is that now the charges are not forced to move in a straight line through a wire. They are free to curve in their pathway, or in the path they travel. All right, So if and only if the force applied at 90-degree angles to the moving particle, so if and only if the force is applied at 90-degree angles to the moving particle, will the particle's direction be changed, but its speed will not. And remember, this is what I taught you for centripetal motion. Always, if you look down on the diagram at 5, the force is at 90-degree angles to the velocity. That is always going to cause circular motion. So it says here, use the hand rules to determine the polarity of charge. When they wouldn't say polarity of charge. Normally they just say determine the polarity on the particle. And what they're asking you for is the charge on the particle. Is it positive or negative? Now, the way you're going to do this, solve this, is you are going to point your fingers, that means your index through your pinky, into the page, because B is represented by X's, which means that B is going into the page. And you're going to orient your thumb in the direction of the velocity. So just pick one of the 3 points on this curve to do that. Now, if your right hand works and gives the force in the proper direction, then it is a positively charged particle. If you have to use your left hand, and remember you use your left hand for negatively charged particles, if it's the one that works, then this is a negatively charged particle. So hopefully you've tried it, and you will determine that it has to be a positive charge. What factors do you think will affect the radius of the circular motion? Again, this is where it's important to understand the forces that you've set equal to each other. So remember, centripetal force is a net force. What is the only force that is causing the centripetal motion? In this case, it's FB, so magnetic force. So what you're doing is you're setting the centripetal force equal to the magnetic force, and if we write out the equations for these, and then we're going to look at the radius only. We have to rearrange the equation for radius. Then, and all I did was I moved this down here and this up here, and canceled out my velocity. So this velocity would cancel out with this v squared. And once I have my equation, it becomes really easy to see the relationships that are going on. So I can see that if m increases, that my radius is going to increase. I can see that if velocity increases, my radius will increase. I can see that if my q increases, my radius will decrease, and q being the charge. And I can see that if my magnetic field strength is increasing, my radius will decrease. Now, of course, you can't write it that way when you're writing out your answers on a test, unfortunately, which would be the easy way of doing it, but you'd have to write those in sentences. All right. So I'll stop this video here